In this lecture video, we're going to look at an example where we test custom hypotheses in the context of a Latin square design. This will be example 4.4, and it refers back to example 4.1. So recall that example in which an experiment was conducted to evaluate and compare the strengths of high-tension insulators made from 4 new clay mixtures, which we're denoting by A, B, C, and D, and a control, which we denote by E. In that example, it was concluded that differences do in fact exist among the 5 treatment means. A natural follow-up to that analysis would be to find out where the differences are. So the first set of comparisons that we're going to perform will be pairwise comparisons among the 5 treatment means. There are 10 pairwise comparisons. We're going to use a significance level of 0.05 for each comparison. And so the first pairwise comparison compares treatment means 1 and 2, and it does that through their difference. And so the null hypothesis is that the difference between mu1 and mu2 is equal to 0, against the alternative hypothesis that the difference is not equal to 0. Because this is a two-tailed test, I'm going to go ahead and utilize the F statistic just because the rejection criteria is a little bit easier to use. So in this case, the F statistic, F calc, is equal to 0.4226 rounded to 4 decimal places. The p-value for this test is 0.52788, and that is not less than or equal to 0.05. And so we would fail to reject the null hypothesis. Therefore, there is insufficient evidence at the 0.05 level of significance to conclude that a difference exists between means 1 and 2. All right, the next comparison is between treatment means 1 and 3. Remember that A, B, C, D, and E, instead of using the letters in this notation here, we're using 1, 2, 3, 4, and 5. So 1, 2, 3, 4, and 5 correspond to A, B, C, D, and E, respectively. So now the next pairwise comparison is a comparison between mu1 and mu3. All right, the null hypothesis being that the difference is 0 against the alternative that it's non-zero. In this situation, the F statistic, F calc, is 0.005218, and the p-value is very large, therefore, 0.9436. And so since that is not less than or equal to 0.05, we would again fail to reject the null hypothesis that says that they're equal. And so there is insufficient evidence at the 0.05 level of significance to conclude that the difference between means 1 and 3 is equal to 0. Next, we test the null hypothesis that mu1 minus mu4 is equal to 0 against the alternative that the difference is different than 0. The test statistic F calc is again quite small, 0.6029 rounded to 4 decimal places. The p-value for this test is 0.4524898. Again, that's quite large. It's not less than or equal to 0.05, and so we would fail to reject the null hypothesis. And so again, there is insufficient evidence at the 0.05 level of significance to conclude that the difference between mu1 and mu4 is different than 0. Next, we compare mu1 to mu5, and so this is a comparison of the new mixture A against the control E. And we see in this case that the F statistic is quite large, 35.51, rounded to, say, 2 decimal places. The p-value is therefore quite small, 6.62 times 10 to the negative 5th. And because that is less than or equal to 0.05, in this case we would reject the null hypothesis. And so there is sufficient evidence at the 0.05 level of significance to conclude that the difference between means 1 and 5 is not equal to 0. Next, we compare means 2 and 3, the null hypothesis being that mu2 minus mu3 is equal to 0 against the alternative that it's non-zero. The F statistic in this case is 0.3339. The p-value is 0.5740. And since that p-value is not less than or equal to 0.05, we fail to reject the null hypothesis. And so there is insufficient evidence at the 0.05 level of significance to conclude that mu2 minus mu3 is not equal to 0. All right, continuing on, we next compare the means of mu2 and mu4. All right, so the null hypothesis being that the difference is equal to 0 against the alternative that it's non-zero. The F statistic is very small in this case, 0.01598 approximately. The p-value is 0.9015, so very large. It's certainly not anywhere close to being less than or equal to 0.05, and so at the 0.05 level of significance, there is insufficient evidence to conclude that a difference exists between means 2 and 4. Next, comparing means 2 and 5, so this would be the comparison of the clay mixture B with the control E. We see in this case that the F statistic is quite large, 28.19 approximately. The p-value is 1.856 times 10 to the minus fourth. All right, so that's quite small, certainly less than or equal to 0.05. And so we would reject the null hypothesis. And so the conclusion would be that there is sufficient evidence at the 0.05 level of significance to conclude that mu2 minus mu5 is not equal to 0. Equivalently, there is sufficient evidence at the 0.05 level of significance to conclude that a difference exists between mu2 and mu5. Continuing on, comparing means 3 and 4. All right, and so we see here that the F statistic is equal to 0.4960 to 4 decimal places. The p-value would be 0.4947, and that is not less than or equal to 0.05, and so we would fail to reject the null hypothesis. And so there is insufficient evidence at the 0.05 level of significance to conclude that mu3 minus mu4 is not equal to 0. Next, comparing means 3 and 5. So this would be a comparison between the clay mixture C and the control E. In this case, the F statistic again is quite large, 34.66, let's say. The p-value for the test is 7.401 times 10 to the minus fifth, so very, very small, less than or equal to 0.05, and so we would reject the null hypothesis. And so there is sufficient evidence at the 0.05 level of significance to conclude that a difference exists between means 3 and 5. And then finally, comparing or performing the last pairwise comparison between means 4 and 5. The F statistic here is 26.86, rounded to 2 decimal places. The p-value for this test is 2.2833 times 10 to the minus fourth power. Again, that's quite small, certainly less than 0.05, and so we would, in this case, reject the null hypothesis. And so we conclude there is sufficient evidence at the 0.05 level of significance to conclude that mu4 minus mu5 is not equal to 0, or equivalently, that mu4 and mu5 are different. And so the overall conclusions, putting all this together, based on the pairwise comparisons, at the 0.05 level of significance, each of the new clay mixtures is different than the control, but there are no differences, no significant differences, among any of the new clay mixtures. Now, it is also of interest to compare the arithmetic average of the means of the active treatments, that is, the new clay mixtures, against the mean of the control. The next slide shows the hypothesis test for this comparison. And so the null hypothesis is that the arithmetic mean of the treatment means for the 4 active treatments, the new clay mixtures, which would be the arithmetic average of mu1, mu2, mu3, and mu4. The difference between that arithmetic mean and the mean of treatment 5, or the control treatment, that difference is equal to 0. And the alternative would therefore be that the difference is not 0. And so here we have the formula for the F statistic in this case, and looks like I need to put the MSE in the denominator there. So let me do that. Okay, so there we go, fix that right up. And so here is, when we plug everything in, this is what we have, and that evaluates to 49.90 approximately. The p-value for this test would then be 1.312 times 10 to the minus fifth. And since that is less than or equal to the significance level we're using for the test, 0.05, we would reject the null hypothesis. And so there is sufficient evidence at the 0.05 level of significance to conclude that the arithmetic mean of the mean strengths of the new clay mixtures is different than the mean strength of the control. All right, so here is a summary of the comparison results. At least the pairwise comparisons. All right, and so for each of the pairwise comparisons, and I'm expressing the pairwise comparison via a difference, as we did in the null hypotheses. And so for each of these, over here on the far right-hand side, I have the p-values for each of the 10 tests, each of the 10 pairwise comparisons. And in addition, I've got point estimates of the differences between the treatment means, as well as an approximate 95% margin of error. Approximate 95% confidence interval for the difference. And I also have here, as you can see, the 95% margin of error associated with each of these point estimators. And it's using the point estimate and the margin of error that we get the lower and upper confidence limits. So 0.72 minus the 2.4133 would be equal to the negative 1.6933. And if we add that margin of error to the point estimate, then we get the upper confidence limit. And so you can see here that the confidence interval does not include 0 if and only if the p-value is less than or equal to 0.05. And so, for example, these p-values are not less than or equal to 0.05. All right, but this one is, okay, it's very small, and this confidence interval does not include 0. Then we look at the next two rows, and this interval contains 0, as does this one, and correspondingly, these p-values are not less than or equal to 0.05. Next, we look at this row. You can see that this interval does not include 0, and corresponding to that, this p-value is less than or equal to 0.05. The next row has a confidence interval here that does include 0, and this p-value is 0.4947. So that's not less than or equal to the 0.05, which is our significance level. And then finally, the last two rows corresponding again to comparisons with the fifth treatment. And again, I've got a little typo there. Let me fix that. All right, so these are both comparisons with mu5. This is a comparison of mu3 and mu5. This is a comparison of mu4 and mu5. Both of these confidence intervals do not include 0, and corresponding to each of these p-values are very small, both being less than or equal to 0.05. All right, so here is some SAS code that we can use to perform these comparisons. The pairwise comparisons, as well as the comparison of the arithmetic average of the 4 active treatments with the mean of treatment 5. And I also have the code over here to enter the data into a SAS data set. And once you have that, then you can run this code here to actually perform the analysis. So the first 3 rows tell SAS how to do, it instructs SAS about the model, in particular that this is a model for a Latin square type of design, and that performs the analysis of variance. And then these estimate statements construct point estimates, and because they have the /CL option afterwards, they also perform or calculate confidence intervals. And then if we look at the next page here, the next slide, we see the output of SAS. So we have point estimates for each of these linear combinations or linear functions of the treatment means. We have the lower and upper confidence limits, 95% confidence limits, for each of those. We also have the p-values, all right, for where the null hypothesis for each one of these would be that the corresponding linear combination of the treatment means would be equal to 0. So just as we perform these hypothesis tests, that's what these p-values are testing. And so if you compare the results we have here on this slide with what we got by hand, you'll see that we have the same results. So that is the end of this example, and it demonstrates many of the types of hypothesis tests that we can perform in the context of a Latin square design. We didn't do all of them, but you can try to perhaps use the data to test some of the some additional hypotheses. And so we will continue on with the next topic in the next lecture video.